Hello, my name is Isabella and I will be your host today for another mathematics video brought to you by RJ. In a previous video, I derived the integer test function. However, this function considers all pre-images, not just integer pre-images. This brings me to my first question for you today. Can we modify the integer test function so that it produces a 1 only when its given function's pre-image is an integer and the given function's image is an integer? Before, we chose the identity function as an example, but it's obvious that every integer image has an integer pre-image. So, let's choose a different but simple function where we know that not every integer image has an integer pre-image, such as x squared. If we put this inside the integer test function, we get, let me graph this. As we can see, not all pre-images are integers when the image equals 1. This is our issue, but can we fix this? Yes. I said before that the identity function has the property that every integer image has an integer pre-image. When we multiply any number between 0 and 1, including 1, by a number between 0 and 1, excluding 1, we obtain a number between 0 and 1, excluding 1. I'll leave that for you to check, but this helps us get exactly what we want. So, all we need to do is multiply this integer test function by the integer test function of the identity function. Let me graph this. This time, pre-images are only integers when the image equals 1. So yes, we can modify the integer test function so that it produces a 1 only when its given function's pre-image is an integer and the given function's image is an integer. This comes in handy when we want to know when both the pre-image and image are integers. For any function, we just multiply the integer test function of that function by the integer test function of the identity function, which looks like this. The floor function is very helpful here, but becomes troublesome when evaluating the integer counting function. So, my second question to you is, what happens when we remove the floor? And no, I'm not talking about pulling up carpet or removing tile. Just don't look down. Let's use the example we just used. If we remove the floor, we get, let me graph this. All we care about is when the image is 1. If we expand this out and set it to 1, we get, oddly enough, if we set this term to 1, we obtain the same solutions as the entire equation. Why? To derive the integer test function, we modified the general oscillating function so that the images would be between 0 and 1. Since we only care about when the image equals 1, we can change the 1/2 to 1 for both the height and vertical shift, as these only affect the vertical. Let me draw the graph to show you. Obviously, the two graphs are not equal, but the images equal 1 for the exact same pre-images. Therefore, with some rearranging, we can rewrite this as, this looks much simpler, right? Let's make it even simpler by transforming it into a product by using the property. Let us set y to 2 pi x squared and z to 2 pi x. Substituting these in, we can now substitute this into the equation up here and do some rearranging to obtain, since this is 1, together these must equal 1. The only way that can happen is if this term equals 1 or -1, and this term equals 1 or -1. To see when this happens, let's solve for x in all 4 cases. I'm just going to write the end results. I'll leave it to you to check how I found the results. K, L, M, N are integers here. The first x is when the first term equals 1. The second x is when the second term equals 1. The third x is when the first term equals -1, and the fourth x is when the second term equals -1. Now we need to determine when these two intersect and when these two intersect. The intersection of these two terms is all of the integers. The intersection of these two terms is the empty set. Finally, we take the union of these. We have our answer. For which values of x is x squared an integer and x an integer? All integers, which is exactly what we get using the starred integer test function. So, yes, it is possible to remove the floor from the integer test function if we use this process. Now, this begs the question, how can this process help us with integer counting function? Stay tuned for a future video. I hope you enjoyed this video. Thank you for watching.